In this problem, we have to explain the linearity property and first shifting property of Laplace transform, and by using this first shifting property, we have to find the Laplace transform of e to the power of minus t into t plus 1 whole square. So first we will derive this formula. We will write theorem, linearity property theorem. So linearity property. A statement of this theorem. In this, we will take two functions f of t and g of t. By the definition of Laplace transform, we have integral 0 to infinity e to the power of minus t into f of t, which is equal to f of s. Similarly, here we will take two functions f of t and g of t, and we will take two variables a and b. So in the statement we will write if the function f of t, if f of t and g of t are two functions whose Laplace transform exists, if a and b are any two constants, if a and b are any two constants, then we have to prove this condition. L of a into f of t plus b into g of t is equal to a into L of f of t plus b into L of g of t. So in the proof we will write, by the definition of Laplace transform we have L of f of t is equal to integral 0 to infinity e to the power of minus st into f of t dt. This is also equal to f of s. So here we have to prove L of a f of t plus b g of t is equal to a into L of f of t plus b into L of g of t. So in place of this f of t, we will substitute a f of t plus b g of t. So this becomes L of a into f of t plus b into g of t is equal to integral 0 to infinity e to the power of minus st. In place of f of t, again we have to substitute this function a into f of t plus b into g of t into dt. Now we will separate each term. We will multiply a f of t with e to the power of minus st. Similarly, e to the power of minus st is multiplied by b into g of t. So left hand side, L of a f of t plus b g of t is equal to integral 0 to infinity e to the power of minus st into a f of t plus e to the power of minus st into b g of t into dt. Now we will separate these two terms. Keep left hand side as it is. L of a f of t plus b g of t is equal to integral 0 to infinity. I am writing a first. A into e to the power of minus st into f of t dt plus integral 0 to infinity b into e to the power of minus st g of t dt. Now take this a outside. Here also we will take this b outside the integration. L of a into f of t plus b into g of t is equal to a integral 0 to infinity e to the power of minus st f of t dt plus b into integral 0 to infinity e to the power of minus st g of t dt. Now by the definition of Laplace transform, we have this value is equal to f of s. So here we will write f of t. Similarly, this function becomes g of t. So L of a into f of t plus b into g of t is equal to a into this function is L of f of t plus b into L of g of t. This is our linearity property. Now we have to prove first shifting theorem. This is the second theorem of Laplace transform. First shifting theorem. The statement of this theorem is if L of f of t, Laplace transform of f of t is equal to capital F of s, then we have to prove that L of e power of at into f of t is equal to f of s minus a. This is the statement of the theorem. Now we will write proof. By the definition of Laplace transform, we have L of f of t is equal to integral 0 to infinity e to the power of minus st f of t into dt. This is our Laplace transform definition, and we know that this is equal to capital F of s. Now in place of this f of t, we are taking e to the power of at into f of t. So substitute here L of e to the power of at into f of t is equal to integral 0 to infinity e to the power of minus st into e to the power of f of t dt. So L of e to the power of at into f of t is equal to integral 0 to infinity. Here bases are same, so we can add their powers. So it becomes e to the power of minus st plus at into f of t dt. Now L of e to the power of at into f of t is equal to integral 0 to infinity e to the power of, from these two terms I can take t common, so it becomes minus s plus a into t into f of t dt. But in the definition of Laplace transform we have minus s into t. So from here we can take minus sign outside the bracket. We get L of e to the power of at into f of t is equal to integral 0 to infinity e to the power of minus of s minus a. Minus into minus plus a, minus into plus minus s. So we are taking this negative sign outside the bracket into f of t dt. We know that this is equal to f of s. Coefficient of t is minus s, so we are writing f of s. Here coefficient of t is s minus a, minus of s minus a. So in place of s we will substitute s minus a. So this is also equal to f of s minus a. Therefore Laplace transform of e to the power of at into f of t is equal to f of s minus a. This is the second theorem. Now we have to find out the Laplace transform of e power of minus t into t plus 1 whole square. Okay, one more thing here. If it is plus a, e power of plus at, on the right hand side we get f of s minus a. Suppose if I take L of e power of minus at into f of t, then it becomes f of s plus a. Minus sign. When we have minus sign on the left hand side, we will write plus on the right hand side. If it is plus at, then we will write s minus a. So in the problem we have to apply this condition. L of e power of minus at f of t is equal to f of s plus a. So our question is f of t is equal to e power of minus t. Minus t means coefficient of t is minus 1. A, the value of a is minus 1 into t plus 1 whole square. T plus 1 whole square means it is of the form a plus b whole square is equal to a square plus 2ab plus b square. So t plus 1 whole square, its expansion is t square plus 2t into 1 plus 1 square. So we can write t plus 1 whole square is equal to t square plus 2t plus 1. So in place of this t plus 1 whole square, we will write this expansion. F of t is equal to e power of minus t into t square plus 2t plus 1. Now taking L, Laplace transform operator L on both the sides. So L of f of t is equal to e power of minus t, we are keeping as it is. Okay, before this we have to write L, so it is t square plus 2t plus 1. Now we will separate each term. L of f of t is equal to L of, it is e power of minus t into t square plus 2 e power of minus t into t plus e power of minus t. Now we get L of f of t is equal to L of e to the power of minus t into t square plus 2 into L of e to the power of minus t into t, last term, plus L of e to the power of minus t. Now we have to apply the formula. L of e to the power of minus at into t to the power of n. We get n factorial by s plus a whole to the power of n plus 1. This formula we will apply for the first two terms, where n is equal to 2, here n is equal to 1. In the first term we are taking the value of n is equal to 2. In the second term the value of n is equal to 1. And for the third term we are taking Laplace transform of e power of minus at is equal to 1 by s plus a. So a is equal to minus 1. So here we will write L of f of t is equal to n factorial. N factorial means 2 factorial. It is 2 factorial by s plus a. So it becomes s plus 1 whole to the power of 2 plus 1. This is first term. In the second term we have 2. We are writing 2 outside. The value of n is 1. So 1 factorial by s plus a is also 1. S plus 1 whole to the power of n plus 1 means it is 1 plus 1. Third term is 1 by s plus a means it is plus 1. Now 2 factorial, we will write its reverse order, 2 into 1. L of f of t is equal to 2 into 1 by s plus 1 whole to the power of 3 plus 1 factorial is also 1. So it is 1 by s plus 1 whole square plus 1 by s plus 1. 2 ones are 2. So the required answer is L of f of t is equal to 2 by s plus 1 whole cube plus 2 ones are 2 by s plus 1 whole square plus 1 by s plus 1. In this problem we have 3 terms, 3 bits. First bit is, in the first bit we have to prove linearity property. In the second bit we have proved first shifting theorem. In the third bit we have solved this problem.